Good morning to everyone. My name is Madeleine Gácita, and I'm from INPE in Brazil. And I would like to present to you today, this morning, my work about the hygroscopic behavior and CCN, or cloud condensation nuclei activity of biomass burning in Brazil. Some results. Before starting, I would like to acknowledge my co-authors in this work, Professor Scott Martin from the Harvard University, and Dr. Carla Maria Dongo, and Dr. Saulo Freitas from the National Institute of Space Research here in Brazil. Before everything, I would like to talk about biomass burning that, as many of you already know, and some of my colleagues here, previous presentations already introduced, hopefully. We all know that biomass burning is a major source of aerosols in tropical America and also in other regions in the world. And with 271 teragrams of carbon per year, is one of, it represents 50% of emissions in the world. So, biomass burning aerosols can act as CCN, and they are present in significant quantities. This is one Sol campaign, and this is a campaign in Beijing. And the campaign, a small campaign in 2002 in the dry season in the Amazon region, is below, just below this number, so there are a significant amount of CCN, as aerosol, the biomass burning aerosol that can act as CCN. However, the hygroscopicity of these aerosols is not very high. We can, like values between 0.01 and 0.55 have been observed, but we could say that a typical range would be 0.1 to 0.3 hygroscopicity parameter. So they don't have a very high hygroscopicity, however, they are present in significant quantity. So I'm a modeler, and my question was like, okay, so I want to model biomass burning aerosol very well into my model, because that's one of my main objectives in my thesis. And how am I going to do that? First thing, I need to have very well the hygroscopic properties of this biomass burning into my model, so I can have well represented the CCN activation, both in at equilibrium conditions and inside clouds. And this will help me have a better representation into my model of biomass burning aerosols from my region, and also can contribute to global microphysics and convective parameterizations. So, quantifying the hygroscopic behavior, there are many ways to do this, and we choose the hygroscopicity parameter because it's very closely related to what is already in the models, in the parameterizations. This parameter was defined by Peter and Kendrawitz in 2007 through their impact into water activity. And it can be estimated from CCN data, and also for hygroscopic tandem differential mobility data, HTDMA data, having the hygroscopic growth and the dry diameter, so we can calculate this parameter from this data. Biomass burning aerosols have been measured. There is some observations already available from South America. There is this campaign, the LBA CLARE campaign in 2001. There was not that many measurements in this campaign, were just like some isolated days, but in total like 691 observations. This includes observations for all dry diameters, freshly emitted aerosols, and 523 observations of aged aerosol. From the LBA small campaign 2002, there were already like a larger collection of observations with a total of 3,854 for the dry season and 2,534 for the dry to wet transition period. So I'm showing here very briefly this data that is available, and just prepare the data that is available from Rees et al. 2006. So an important thing about this data is that in both campaigns you can observe that there is two hygroscopic groups, one that is barely almost hydrophobic, and one that is like slightly hygroscopic. An important thing is that the nearly hygroscopic group is unfortunately the most abundant. So with this data, I calculated the hygroscopic parameter and for each dry diameter and each hygroscopic group. And we can see that when we do a weighted average and weighted by abundance and also by number of observations, we can see that we have fairly low values. Like when we have smoke plus clear, we have 0.07, and when we have only smoke, 0.062. So I will ask you to keep these numbers in your mind just for a one more slide. So when we use this number to estimate the CCM population under equilibrium conditions, we can use either a detailed form that relates the saturation ratio to the hygroscopicity parameter and the dry and wet diameters, or we can also use for some conditions that have been proposed as like a hygroscopicity parameter bigger than 0.2. And this is supersaturation of less than 1%. We can use this simplified form. And this simplified form is very important because it's the starting point for several parameterizations that have been created. An important thing was that this threshold was higher than our values. So the first thing that we considered was, okay, what happens now? When we found those results, can we use this parameterization? Can we use those the calculation, the normal calculations with these low hygroscopicity values? And that was one of the things that we need to answer first. So we first estimate the cloud condensation nuclear population, the equilibrium conditions, and we considered 5 approaches. Basically, we consider the detailed or the simplified form of the color equations, and we consider either a total weighted average, like this 0.02 when we are considering smoke, or an average for each hygroscopic group, and then considering the relative abundance of each one of these groups. What happens when we consider the specific hygroscopicity parameter for each diameter and each hygroscopic group. So we consider these 5 approaches. And we have an amazing result that is that there are few differences at equilibrium conditions. And of course here I'm talking about supersaturation levels, because below saturation we do find some significant difference, like at 90% of humidity. There are significant differences between both approaches, but at supersaturation conditions, we found almost no difference. Like the standard deviation, the higher standard deviation that we found in this result was 200 particles per cubic centimeter, which is fairly low considering the values. So what happens when we consider conditions outside equilibrium? So we did the calculation for a cloud model that is basically similar to what is everywhere else, but we use the equation, the detailed color equation, to estimate the growth to initial conditions, and we consider 200 beams spread geometrically following a volume ratio size distribution, and also we consider particles bigger. The particles bigger than the smaller activated particle at the time of maximum supersaturation are considered activated. And for the parameterization of adult result GAN, we basically consider it like as it is described in the articles. And the results for the dry season in the Amazon region are the maximum supersaturation is fairly close determined by the parameterization is fairly close to the numerical cloud model, increasing a little bit for high updraft. And for all modes, when considering the aerosol population as a whole, and this is very important for us, we find that the bias of the model comparing, of the parameterization comparing to the detailed numerical cloud model is fairly constant through almost all the medium to high updraft considered, although when considering each mode separately, we can find a little bit higher differences. For the dry to wet season period, we find also a similar behavior for the maximum supersaturation, a little bit higher here, and also the same behavior here. So starting from 1 meter per second, we have a fairly constant bias. So there is obviously a dependence, but the dependence with the updraft, I mean the bias is almost equal, and this is very good because it allows us to estimate the uncertainties what we are having. So my next question was, okay, what is the paper of the role of the low hygroscopicity in this? And we have that is almost, like, I mean, it's secondary, and size really matters. I mean, there is a dependence of hygroscopicity, but this dependence is not reflected in the bias, and this is very good news for us. So my conclusion is that the hygroscopicity of the aerosols in the Meson region was on the lower side of the range observed elsewhere for biomass burning, and this is important. So if we want to have it right, we have to put the numbers that we have and not the, like, a general number. And not significant difference arose from the use of a detailed or a simplified approach in the estimation of CCN in equilibrium for supersaturated conditions, although the growth, the hygroscopic growth at undersaturation conditions does change. And the hygroscopicity only is not able to explain the difference between the cloud model and the parameterization of Abdul-Razak results, and size have a big influence on this. And now we need to conduct more tests to assess better the role of number concentration and the thrust velocity, and these tests are already in progress. And I promise that in the future I will have for you some nicely shadowy colored maps. So that's all. Thank you.
Thank you, Madeleine.
Before finish, I would like just briefly to acknowledge, to thank the IGAC committee, and also for PSP to allow me to conduct this work, and also to be present here with you today. And Harvard institution that received me nicely for 8 months, and also my institution. So thank you very much, and I'm very excited to be here today.
Thank you. Do we have a question for Madeleine? One question.
I enjoyed this very much, and I like the conclusions outside.
Sorry, I can't hear. Could you
wait for the mic?
I enjoyed this very much, and I like the ideas about size. You know, one of the things that I'm actually considering a lot myself is this question about the hygroscopicity, what to report. Should you report to modelers something that's just next to the fire, where maybe it's a very hot fire and it's composed of mostly non-hygroscopic particles? Or should you report to them something that they might use that might be something where the fire emissions have been exposed to other, let's say, smoldering, or with other organics, or even to biogenic aerosols that can condense on them? My own experience is it's kind of hard to find on a big scale these very black particles, and maybe the people who did the characterization did the job too well. They got it too close without all the transformation that you might need.
That's a great question, and I have been thinking that myself, because my final objective is to include those results into the model. And the reality is that hygroscopicity does change with the aerosol aging in most cases. So we could do this in several ways, but I will say that the first approach will be at least having it regionally separated, because if we all use only one number for that biomass burning, I mean, it's a 0.01 to 0.55 range. So some results will be bad.